All right, everyone, Mr. Graham here to continue talking about uniformly accelerated motion. I do have the same exact simulation up that we had last time, that we were looking at last time, and I just want to use this to kind of just drive home some points. I'm going to hit play here, and I'm going to turn on the thruster on the left. I'm sorry, the thruster on the right. And so as you'll see, we have a velocity vector that points to the right, and then our acceleration vector will start pointing to the left. So right after we start the motion here, my velocity vector is decreasing. It's getting smaller. And that's because the acceleration vector and the velocity vector point in the opposite direction. You should expect this if you're going in one direction and someone's pushing you on the other direction. You don't immediately travel in the other direction. You actually have to slow down first. And as we'll learn, the force that causes the change, any force that causes a change in motion will point in the same direction as the acceleration. And so we have the acceleration that points in the opposite direction to the velocity, and so it slows down. And just like in the last video, at the point that the object stops is right about there. So now my velocity is 0. So on my velocity versus time graph, that's when we cross the t-axis, and that's when our parabola reaches its vertex. That's where the slope is 0. If the slope is 0, the velocity is 0. That's one thing to remember on a position time or distance time graph. The slope is the velocity. So any descriptive term you can apply to the slope can be applied to the velocity. If it has a positive slope here, but it's decreasing, then I can say I have a positive velocity here, but it's decreasing. If I have 0 slope, I have 0 velocity. And then as it continues, the motion continues, the acceleration vector and the velocity vector now point in the same direction, therefore my velocity will increase. And I start getting steeper on my position versus time graph, but in the negative direction. I have a negative slope there, so I have a negative velocity. And notice now I'm going down into the 4th quadrant on my velocity time graph, indicating that I do, in fact, have an object traveling in the negative direction, okay? And again, I get a nice parabola on my distance time graph, and I get a nice linear graph for my velocity versus time graph. The slope doesn't change here on my velocity versus time graph. The slope doesn't change. And on the velocity time graph, the slope is the acceleration. So if my slope is negative, I have a negative acceleration. If my slope doesn't change, my acceleration doesn't change. And we can see that our acceleration vector here does not change its size. And therefore, it has uniform acceleration. It's traveling under uniformly accelerated motion. Now check this out. Here's a slightly different situation where I have a velocity up a ramp and the acceleration actually points down the ramp. Now I don't need a thruster here. All I need is gravity. Gravity is actually going to create this acceleration that points down the ramp. Something to keep in mind when we study motion on ramps, which we're going to do quite a bit in this class, it definitely helps to think of your coordinate axes as being parallel and perpendicular to the ramp. One of the things that Newton and Einstein kind of assumed is that especially Einstein, when he was working out relativity, you might have heard of it. It doesn't matter what coordinate system you use. You can choose whatever coordinate system you want to make your measurements, and you'll fully be able to describe reality just as good as someone that uses a different coordinate system. But as we'll learn when we study forces, whenever we angle our coordinate systems, whenever we change them to align with the ramp, it makes the math that we're going to learn pretty soon much easier to deal with. I'm talking much easier. So you actually want to do this. So I would say in this particular coordinate system, I actually start with velocity in the positive x direction. I don't know what's going on with my video, but it keeps cutting out. Sorry about that. At least you don't have to look at my ugly mug. Okay, so if I hit play here though, and what I want you to do is remember what the motion graphs looked like for the last graph we had, or the last type of motion. We had a nice parabola on the, hold on one second. Let me get this up. I'm sorry, guys. I'm still, again, learning this stuff. Give me 1 second. All right, so I got my graphs up here now. I'm going to have my position in my new x direction, which is up the ramp, and my velocity versus time. Let me get rid of this real quick. My velocity versus time graph, which will also reflect the motion in the x direction, which, again, I've now defined as up the ramp. And what you'll see, happened real fast here. Let's do it again, but let's slow it down. Notice those graphs look identical. They look identical to what we saw with the thruster situation, right? And what I'm trying to show you here is that anytime you have uniformly accelerated motion, it's going to look the same. Now, sometimes we slope from the negative quadrant to the positive quadrant on our velocity time graph. Sometimes our parabola is inverted and it makes a U shape. But if we have uniformly accelerated motion, we always have a parabola for our position time graph or distance time graph, and we have a linear graph for our velocity time graph, and that's exactly what we see here, okay? So I'm gonna run this one more time and pay attention to where things are at on the graphs, specifically the velocity time graph. We start with a high velocity, and immediately after it starts going, it slows down, as things tend to do as they're rolling up a ramp. And when it comes to a stop, when the object comes to a stop, that's when the graph crosses the horizontal axis, which is the time axis, crosses the time axis, and our position time graph becomes horizontal, right? That's the vertex of our parabola. Now it starts accelerating down the hill. Again, acceleration, velocity point in the same direction, therefore it's going to be speeding up just in the negative direction, okay? But the graphs look identical. They look identical. In fact, the graphs for a motion that we're definitely very familiar with, let me erase those wonky coordinate axes here. If I was to put coordinate axes here, I'm gonna use the standard coordinate axes because now the ground is in fact horizontal. So there's my y-axis, and then maybe my x-axis right here. And notice the initial velocity is in the upwards direction. So I would call this my initial position in the y direction, and my graphs are actually going to reflect position in the x direction and velocity, or sorry, in the y direction and velocity in the y direction. And look what we get. The same exact motion, or the same exact type of motion graph. Not the same motion, but the same exact type of motion graph. And let's slow it down so we can see this in a little more detail. So I start with an initial velocity pointing up. Velocity and acceleration are pointing in the opposite direction. You might guess what causes this acceleration. That's gravity. And so it slows down on the way up. And when it reaches zero velocity, that is where the velocity time graph crosses the time axis, the horizontal axis. And again, that's where my position time graph or distance time graph becomes horizontal at the vertex of the parabola. And then it starts speeding up in the opposite direction. Now that the acceleration and velocity point in the same direction. But the motion graphs, again, look identical. They look identical. And an interesting note here, Galileo is considered the father of modern science. Galileo was the one that first studied motion in this way by trying to produce graphs. Obviously didn't have computers back then. They didn't even have stopwatches or clocks. They had what he used for his timer. He actually tended to use his pulse for his timer. So not the best timing mechanism, but pretty good. There's no way though to study vertical motion, free fall motion with the limited tools that Galileo had at the time. But what Galileo was able to reason is that this motion here is identical to this motion here. He was able to reason that the graphs would look the same, that the motion would look exactly the same. The only difference would be when you put things on ramps, you would actually get a much slower, the object would accelerate much more slowly. And so he was actually able to study that motion. If you learn about Galileo, he did his experiments by rolling balls and cylinders up and down ramps, as opposed to just throwing them up in the air, because that motion was just, it happened too quickly for him to take care of, for him to describe fully. So Galileo was figuring this out several hundred years ago, and we're just now learning it now. So, but we get computers and we get nice visuals to help us study them. And because of our technology, we can actually study free fall motion, as you'll see in the next video. All right, that's about it. Thanks, guys.